All right, so 31 says a 4-foot long square ASTM A36 steel bar, 2 inches by 2 inches, subjected to an axial tensile load of 64,000 each end. Parallel to the length, calculate the dimensional change in the bar's lateral and longitudinal direction. So that's axial. So we're looking for an axial change and we're looking for a transverse change. So that's what the quiz was. So to get axial change, we should always check, and I haven't harped on this enough, so I'm going to harp on it more. We should always check the tensile stress before we do anything. Because if the tensile stress is over the yield stress or some kind of allowable stress, then we can't do anything. Like it'd be a really crummy problem for me to give you like on an exam or a final, but I'll be harping on this a lot. If the actual stress on the thing is over the yield or some kind of allowable, we can't do anything. We cannot predict anything. So I checked it first. I took the 64,000 and divided by 4 because it's 2 by 2. P over A gave me 16,000. That's well under the 36. So we're good to continue to work on this. Okay. So check the stresses right away on all the problems. Make sure they're within the allowables. So if they have given us some other allowable, we'd want to make sure it was under that. It is. It's 16,000. A36 is 36,000 yield. So we're good. This was the quiz. It came up on that Friday. Week 4, quiz 3, out there. So it's hidden now. It came available and then it goes away. So it was available on the 22nd. So I'll open it back up. Actually, no, I'll give you a makeup quiz. So there's a few of you that missed it. So we'll do a makeup quiz at some point. Remind me though, or I'll forget. Yeah, there was a few of you. Your screen sharing is paused. Resume share. Oh, there we go. All right, so let's keep going on it, even though you haven't seen it before. So the problem's asking for lateral change and transverse change, both. So before we can get any kind of change in the cross section, we have to get the axial change. So the way you get the axial change is you use E, because we know the modulus is equal to the stress divided by the strain. If we can get the strain, then we can get the axial change. Okay, so we know E because we know the material. We know the tensile stress because I just calculated it, P over A. So I just solved for the strain. This is the axial strain. So I just put 16,000 over 30 million E, 30 million, and got 0.000533 for the strain. So when you get the strain, you're one step away from the actual change in length because strain is equal to the change divided by the original. This is all axial, or what they called longitudinal. Same thing, long. Just think of long. So then I actually want this. I know this, 48. And now I know this because I just calculated it. So I can say, oh, the change in the axial length is going to be equal to 48 inches times my 0.000533 inches per inch. And that is 0.0000533. 0.2558 inches. Because this is unitless, so we have inches left over. So that's how much it stretches. You got to find that first before you can find out how much the cross section changes. Red dyed, maybe blue works. So there was a relationship between the strain along the axis and the strain on the transverse, right? Anyone remember what that is? Yep. Poisson's ratio. Yep, Poisson's ratio. So mu equals the strain in the transverse over the strain in the axial. So that's the material property that helps us find that cross-sectional change. And we know that strain is equal to a couple things. It's equal to stress over E, but it's also equal to the change over the original, right? The change over the original. So this is in the transverse now. So this can get subbed into there. And then we can go for this change in the transverse. We already have the change in the axis, but this gives us the cross-sectional change. So we can solve for this first. This is 0.25, getting low. So I can say, okay, my transverse is equal to 0.25 times the axial strain. That was this one. Zero, 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 1325. Change delta L, original length. Yeah, so it's always delta over L. And this is my little t because I'm thinking transverse. Because yeah, now we're going to plug it in here, right? And we're going to solve for this. So if I want to know delta transverse or the change in the cross section, then I solve for it. That's going to be the original length times the transverse strain. So two by two. So it's 2 by 2. So I know that transverse direction or dimension is 2 inches. And then I know this strain is 0.0001325 inches per inch. So we did that here. Yeah, I solved it. I solved it out. So I just boiled this down. Yeah, that's how we got that. This is strain A. Because I took the stress divided by E. So this is EA, right? This is stress A. This is same thing. right? And then I multiply it times mu times to get this. So I just solve this for this, and it's going to be strain A times mu. Strain A is that times mu. I'm letting them look. So the other thing you could have in here, what else could you have in here? You could have, no, it'd have to be this. Good? Yeah. Is it going to be a different, same number, a different number, you think? Okay, it should be the same number. Yeah. All right, let's keep going here. All right, so then delta T equals 2 times. So 0.000265. Is that what you got? Yeah, that's rounding for sure. Yeah, there's probably other ways, like you could boil this down and transfer it in, so I'm sure. Most important thing is you got to find axial stuff first, and then you got to use Poisson's ratio to get to transverse. Correct. That's correct. Ah, you did the area. That's all good. It's all good. Yeah, so this is like kind of all about Poisson's ratio right here. And a lot of times you do want to know both how much it stretches and how much it reduces. So it's a good thing to be able to work through. Any other questions before I take it off here? Yeah, let's do it. Uh-oh. Maybe the book's wrong. Maybe you're wrong. We'll see. Let's do number 11. 11. Yeah. 2 or more materials. Then we see, what do we have? A wood post. Oh, I see it. Oh, no, I don't. There's no picture, is there? Yeah. Short wood post reinforced on all 4 sides by 836 steel plates. 2 plates are 4 inches by 1/8 thick, and 2 plates are 8 by 1/4. Tricky. The heck? Why not just make them the same plates, people? That's what you said, right? So it's a 4x4? No, 4x8. All right, bad scale here. Sorry. And is it really 4x8, or did you? Using nominal dimensions, calculate the maximum axial compressive load. Okay. Yeah, nominal means use the 4, use the 8. So nominal means use the numbers typically. So I'm guessing they used 4x8, like 4 times 8. Yeah. So if you used a different area, that could be why your number's different. It's a lot different. It's still by like, okay. 5K. All right. I would use the 32. So 2 plates are 1/8 inch. 4x8, that's these. And 2 plates are 8x1/4. Using nominal dimensions, calculating the maximum compressive load that the member can safely carry. The wood is southern pine. The allowable stress is 20,000 for the steel. So good, think I got it all. So we need to look up, what'd you get for the compressive stress of southern pine? Because we have to have that, right? Okay, so that's E. Yeah, so what was E again? Yep. And then the compressive stress. Okay. And then we have an allowable stress for the steel at 20,000. And then do we need E for steel? Okay, what did we get? All right. So that identifies material A and material B, correct? Because that's one of the first things we have to figure out. Which one's A, which one's B? Which one is A? Steel is A. So this is material A. So then we want to go search and find that load equation. Yeah, because it asked us what's the maximum load that this can handle, right? Let's see. Let's read it again. Make sure I'm reading it correctly. Using what is 2 plates. Use nominal dimensions. Calculate the maximum axial compressive load. So that's P, right? Load is P. So there should be a P equals equation for multiple materials. Yeah, so what I do is I look at the end of the chapter in the chapter summary, kind of once I've gone through the chapter, then I just reference here for equations. And here's multiple materials. And here's the P equation. So they give it to you in a couple different forms. They give it to you in areas and stress in B and stress in B and A, but then they simplify it down to even a simpler version, stress in B, N, that's the modular ratio, area A, area B. So that's the one I would try and use right there. So stress in B, N, area A plus area B. So that is a combined load equation. And the reason we use stress in B is because it's that weaker material and we're going to drive it up to its limit. So this becomes kind of the limit to this equation. We want to put in that maximum stress for the weaker B material. So P equals, that's going to be 1250 PSI. I'm going to write units out. Right? Because it's going to be the control. That weaker thing is going to be the control. Modular ratio is, what is that again? Yeah, so it's EA over EB. So it's going to be 300 over 17. What is that? Thank you. 17.647. That's the modular ratio. And then area A, that's the steel. So we a little bit of calculating there. So it's going to be 8 times a quarter times 2. So this side looks like it's 4 square inches. And then this is going to be 4 times an 1/8 times 2. Add them together, it looks like 5. Is that what you got? 5 inches squared. These two get multiplied by each other. And then we're going to add to it the area of B, depending on what you used. I'm going to use 8 times 4, 32. Wow, that was scary. I almost didn't know 8 times 4. It's my head cold. And my negative COVID test this morning said it was a head cold. And my negative COVID test 2 days ago said it was a head cold. So there you go. But still stay away from me because nobody wants a head cold. All right. P equals. Anybody have this for me? Or do you want me to catch? This is where are you good here? Yeah.
We got different numbers and the book is a different number.
From both of you?
Yes.
Oh,
Yeah, I think this is just a bit confused. I used the table number, the 25 area, but it's still higher than what the book is. Yeah, this is closer to what the book is.
I'm getting 150.3K. What's the book get? 136K? Oh. That's what we got. That's what I got. Exactly. Because I wrote kips, right? So that's 150,000 pounds. And I just rounded I got 293 also, but I just rounded it to 3. All right, I'm going to read it one more time, see if I missed anything. We've got a wood post. We have 2 plates on each side, and we have their sizes correct. So you're saying if you change, it doesn't change it?
I got 142,044.
And they got 136? Yeah, that's still substantially different. All right, I don't know. The good part is I have the solutions manual. Bad part is that's not here with me, so I can't like look right now. But I'll post up what they put down. I could probably, yeah, I could do it. It's probably on my laptop, but we'll run out of time if I do that. But I'll identify and put it up so you can see what the heck they did. I'm pretty comfortable with that though, so. There's a big old exam on Thursday. Yeah. How you feeling about that? Yeah, so you can use notes and you can use your book. Both of those. Yeah, absolutely. Yep. 2 hours. If that works. If it doesn't, then reach out to me and we'll do it some other ways, some other how. Okay. It's not on a laptop. But oh, you have to have Wi-Fi to use it, so the book's not downloaded onto your laptop. I guess try downloading it, see if that works. Brian, you think she can do that? Like that's an option? Yeah, so it might just be online. That doesn't make sense though.
Yeah, and I'll never do it again because I need that book.
Can we get into that website through one of these computers? So the only, I mean, I'm just hesitant letting you take it not here because everyone has questions. So you can't ask a question if you're somewhere else taking it. That's a big disadvantage, so. Just the chapters you want type of thing? Yeah. Potentially. If you email it to me, I can print it for you because I have that. You just need it for the equations. So if you have all the equations written down, which I highly recommend, it's not real great spending time looking for equations. So either tab your book, if you have a book like this, tab it, or give yourself a. I can do that. Yeah. Yeah. Or just send me chapters and I can, yeah. Some of the problems will be a lot like your homework problems. So on those problems, if you can identify that, you know, you can use your homework problems for sure. Some of the problems are going to look like homework problems, but they're not the same. So the disadvantage to you getting to use your homework is you might look for a problem that looks just like this one and then just copy the process. That's not going to work on some of it. You're going to have to think your way through it. So just be careful with that. There'll be like 8 of them and like 5 of them will be very straightforward and simple. Like you won't have that much to do. And then 3 of them will be, you'll have to work your way through stuff. There could be one that has a little statics, but I'm not going to give you like a whole statics problem before a strengths problem. Yeah. Yep. Yep. Absolutely. Yeah, you might.
That's a good question.
Centroids, inertias. Ooh. Maybe. I mean, I haven't made it yet. I didn't even think about that. So I don't usually start this class in that, but probably not, I would say. No, 9, probably 9. I think 9 is stresses. Yeah, 9, 10, 11. Yep. We haven't got to bending stress yet, so not inertia. We'll kind of revisit inertia when we get to bending stresses. Yeah. And the bending stress equations MC over I. So that's when we'll need I again. So yeah. Yeah. So let's finish 11. Because there's one more area of 11 I want to do. There's 2 more areas of 11. We're not going to do, I think they have combined stresses. No, they have inclined plane stresses. I think that's kind of hokey. But we are going to do concentrations. So stress concentrations. So let's do that. Yeah. It could be on the exam. Obviously, I'm not going to emphasize it because we're just doing it once. And you're going to do a homework on it, but it's not real difficult, I don't think. And inclined planes is not either, but it's just, there's not a lot of great application. So that's inclined planes. Looks really complicated, but it's absolutely not. But really, you're not going to do inclined planes when you get out there. Like if somebody says, hey, calculate this stress on an inclined plane, like, dude, that's not my job. That's some guy with gal with a master's degree type of thing. But we do want to think about stress concentrations. That's what this is. So stress concentrations happen when you have a reduction in area, which makes sense. Like we know stress is P over A. And if that area gets smaller, then it's P over smaller a, right? The stress goes up. So it's not linear though. Yeah, it's not just a straight ratio. Like, hey, the area reduced this much, So now there must be a new stress. There's a new average stress, but the concentration goes up nonlinear. Here's a graph of it, right? So as we change the cross section, and we change the cross section all the time. We put holes in things because we want to mount things, right? We want to mount a motor here or a hydraulic pump there, or put a bumper on here, or put a tow hitch on your car, right? Well, that puts holes in frames that is going to create a stress rise. So we have to consider that. So this is how we do concentrations in this class. Like I said, they're not a linear function, they're a calculus function. So we can do 3 of them without calculus, pretty straightforward. And these are the 3 most common ones. A hole. So when you poke a hole in something, it creates a stress rise. So this little graph here, that's our normal P/A average stress. So this is a little kind of a rotated graph right on the object showing average stress. Okay, when we calculate P/A, that's what we get. Well, here's the hole. We get P/A out here on the edge, way away from the hole. But as we get closer to the hole, the stress goes up dramatically. And then right next to the hole, it's maximized. And that's what we want to know. Like, oh, if we put a 1/8 inch hole in, really tiny, we don't make much stress, right? There's not much of a stress increase. But if we make a bigger hole and a bigger hole, then that stress goes up and we want to be able to calculate it. So the 3 conditions is a hole, equal notches. So a notch and a notch, and then some kind of an area reduction with a fillet. So whenever we reduce the area in a structural member, we try to put nice transitions in, fillets they're called, rounded internal corners like that, to try to keep cracks from developing mostly, because we know there's a stress rise right there. Okay, so all these little graphs are just showing kind of this stress, and that's the equation, Kp/A. Notice that it's P/A, our regular old stress equation, with a K factor in it, inside of it, and then a new area, and it's called the area net or the reduced area. So here is area gross, that's the entire area. Here's area net, that would be the area left over after the hole. So we always have to calculate that reduced area. Does that make sense? Yeah. So the whole game is to calculate an area that's been reduced, a net, and then figure this K thing out for each one of these. Once you have the K, then you just multiply it times that P/A net. That's all there is to it. To get the K, it's a little tricky, not too bad, but it's this graph over here. So let's talk through this graph, which again, is not as complicated as it looks. If we're doing a hole, then you find your hole curve. This is the hole curve. If you're doing semicircular grooves, that was this thing, then that's this graph. And if you're doing reduction in area with some fillets, that's this graph. Okay, where we have K's going up here on the vertical axis, and then the horizontal axis is the R to D ratio, R to D. And you get R and D from these drawings. Okay, so this says 2R circular hole. Obviously, R stands for radius here. R stands for radius here. And R stands for fillet radius here. So R is radius. Okay, D changes, and it's little d. R to little d ratio. So you go up here and you look for little d. Well, here you see half little d. Right? So the other half is on this side, and I've drawn lines in there showing you what little d is. It's the remaining material every time. That's all it is, the remaining material. Same with this one, little d is what's left. And same with this one, little d is what's left. Okay, so the process is figure out your R to D ratio. Go to the graph, go up to your curve, and then read across to K. This is on 232 and 233. So I'm just going to make a problem up. On this critter, I'm going to say this is 4 inches. I'm going to say this hole is 1 inch in diameter. And we're going to put 50K on it. So it's 4 inches wide, 50K pull. We have a 1 inch hole popped in it, and we do need the thickness. So I'm going to say this thickness is 1/8 of an inch. So 1/8 by 4 plate, 50K is a pull, 1 inch diameter. And we want to know what the average stress is, this thing, and we want to know what the maximum stress is. So we know average stress is P over A, right? So my load's 50 kips. And what's my area? Eighth inch times 4 inches. Looks like it's 100 KSI. Right? 50 kips divided by 4 times 1/8 inch. $100 KSI. That's average stress. Everyone see how I get that? No, so I just did this one first. And I did that on purpose because on the test, I'm going to ask you things like, what is the average stress? Okay, that's just P over A. I don't care if you see holes or whatever, it doesn't matter. Yeah. And you move, where this occurs, notice, is away from the hole. The stress concentration only happens right at the hole. Anywhere out here, out here, out here, even right out here at the edge is average stress, right? So the only spot that the stress concentration occurs is right at the hole. So a lot of times we want to know average stress for designing the member. And then we want to know like, oh, I put a hole in it. I better check that. Yeah, Brian.
So probably for simplicity, that would be double, right? So those lines sideways on the circle side. Yeah, so that would be like, it's missing the other half of those lines, right?
Yeah,
It'd be on both sides.
yeah. They're just like, I don't know, putting a graph on the object somehow. Yeah. Yeah. It's like this is 0, and then these are values of stress. This is 0, these are values of stress. All right, so now let's calculate the max. So this is where we need the reduced area. So now I have 1 inch gone. So the area left of the material is 3 inches, right? So my area net is going to be 3 inches times an eighth. So to get this max, I'm going to need my K factor. I'm going to need my 50 kips, and I'm going to need my area net, which is 3 times 0.125. Huh? Yes. Good question. Remember, this is area net. So this was 4 inches, but then I took how much out? 1 inch. So then this now is the area from here to here. So that's going to be 1 inch minus the 4, giving me 3 inches. Times 125 is area. Yeah, I multiplied times the eighth. Right? Because I needed area net down here. Does that make sense, Nick? Okay. So I have everything except for K. So now I'm going to go get K. I know I'm going to need my R to D ratio. What's my radius? 0.5. And what's my D? Careful. Let's see what D was for a hole. D is, this is half a D here and half a D here. D is this area that's left, this length that's left. So again, it's 4 minus 1, which is 3. Because in this little graph over here, it says that this is half D and this is half D. Right? And I know this is 1 inch, so it's got to be the leftover 3 inches. So what's my R to D ratio? Oops, calculator's off. .166. All right, so now I go to the graph. And I go, okay, I got to find my graph, circular hole, that's this top one. And I got to find 0.166. So here's 0.1, here's 0.15, right? And again, it's a graph. You're only going to get so close, and we're all going to get slightly different number, right? But I put 0.16 right here, which is right here, which is darn close to 2.4. So I just went with 2.4. That's my K factor. So from R to D, up to the correct graph, over to get K, 2.4. And that plugs in right there to get the stress max. Is that what you got? 320, if you calculated it? Way higher, right? What did we get for the average? 100? Yeah. Pop a 1 inch hole in it, and now we get 320. That changed. It's, yep, just right here. That's this part of the graph, right next to the hole. But that's why you see, like, if you look at frames that have failed or are beginning to fail, or if you are taking bolts off of something, you'll see cracks propagating out of holes. It's very common to see this kind of action coming off a hole. It's because that's right where the stress riser is. So what's interesting is sometimes you can make this hole bigger and the stress will come down. It's a function of the diameter of that hole and the area and the material that creates the stress riser. So there's kind of a happy hole size to where the stresses will kind of start to mitigate themselves a little bit. But it can really drive up values 3 times. Don't be going drilling holes and stuff. It's not a good thing.